Hello, I am Vitaly Kamlyuk, and this is year 2016. As you can read from my look, I have spent my past 40 years living at home isolation. This is the times after the apocalypse, and this week I wanted to present a Security Analyst Summit, teaching how to use BitScout. I was offered a slot to present about remote digital forensics. This is what BitScout was developed for. However, after the apocalypse, digital forensics does not matter. What matters is survival. So what I'm going to show you today instead is how to use BitScout for survival.
Alright, let's talk about the apocalypse, BitScout, biscuits, and all other things that matter. If you didn't catch it, I am Vitaly Kamlyuk and I'm heading team of researchers in Asia Pacific for Kaspersky. I'm doing malware reverse engineering, non-mechanical forensics, open source development, and a little bit of steam and smoke experiments. The world in 2060 where I live now looks amazing. We still have dating apps and social networking apps that look brilliant. We do have art, it hasn't gone anywhere and I find it fantastic. On the other hand, I remember how silly and cheerful the world looked like. The grass was green, the sky was boringly blue, and everything looked kind of silly to me. The things have changed since then. And the reasons of those are unclear. Some people believe that those were experiments with the new particles that were discovered not so long ago, such as Higgs boson, or maybe completely new particles and new features of nature that was found. But as a result, we've seen that the world, the planet, has stalled in space for a fraction of a second that was enough to cause massive tectonic shifts, and that shifted the ocean and waters and the core of the planet significantly, causing earthquakes and floods everywhere. So all our dirty streets of large cities got cleaned from the garbage by the ocean stepping onto the streets of the big cities. So nowadays the cities look like this. Look how much space we have, and instead of annoying construction works, we have a deconstruction works every day cleaning more and more space. Some people in certain parts of the planet look forward to the first snow in the winter. But here, in our world, we don't need to wait, because we have some kind of, flaky, snow-like thing falling off the sky all year long. And look at these beautiful purple colors and the color of the sky. Our power used to come from the power plants such as this nuclear power plant here, but there was no fun about this because it only caused some administration and maintenance to keep this running. However, now things have changed since most of these power plants collapsed and the reactors melted down, causing explosion and high contamination of the area around it. So our maintenance and care for the reactors is completely different. We do not go there anymore, we can only inspect it remotely with the help of drones and robots, and this is what we regularly do when we see a smoke or an explosion around the reactor. That means some cooling system went down and we need to repair it. Most of the cooling systems are quite reliable, however from time to time they experience some software issues. Given the fact that we cannot really go there and inspect physically, the only thing we can repair it is to do the remote work. And this is exactly what BitScout was created for. So let's look into the control room of such a reactor. What you can quickly spot here is the blue screen of death in the background of the room at one of the systems that is controlling the cooling, the emergency cooling of the reactor to not let it melt down further and not to cause the explosion that leads to the contamination of a larger area around us. So how do we recover such a system from a blue screen? Well, of course, we try to power it off and power it on again. We did it a few times, didn't help, so it goes to the blue screen every time. So how do we fix it? Apparently, we need to start a new operating system from an external media and boot from this external media and fix it remotely. We can connect to this system through the network that still exists and still operational, and this is going to help us. The only challenging thing here is to find where the hell is the USB port in this control room. I'll leave it to you. In the meantime, I wanted to tell that the USB drives are lifesaver tools in our century and in our times, because they help us to revive the dead systems, bring them back to life. So this is exactly what we are going to do today. We are going to build a magic USB drive that is going to save this poor nuclear station from further meltdown. We are going to put a live operating system on this called BitScout, the same as the name of the project, and we will build this from scratch. So let me show you how you do this. Let me bring on my good old lamp terminal. Zoom in a little bit so that you can read the text. So we have internet connection here to the good old internet in 2020 through the time and space channel. We want to build new fresh BitScout disk image to put it on a USB drive. How do we do this? We use Git because BitScout is hosted on GitHub currently. So we do issue command clone with the option recursive to fetch all the dependencies, all the submodules that are included in the project, and then we put the project URL, which is placed on GitHub, like I said, in repository of user Vitaly Kamlyuk /BitScout. So once we clone the source code, which should be relatively fast, let's quickly inspect what we downloaded. So far there are just a few files and directories, and all you need to do to build your new BitScout instance is to run automake script, the automake.sh. If you have already used BitScout somewhere, you can reuse the same SSH and VPN keys that were generated when you run automake, and this is what I'm going to do now. Let me copy this from my previous build and I'm show you what is being copied. So I put my previous build of BitScout in BitScout_prev. So I need to copy this config directory in the current directory, and that comes with some of the configuration files. So other than automatically generated keys that I want to reuse, this slight change that I added in the BitScout build config file. You can of course freely modify it here after you set up BitScout for the first time, but what I wanted to highlight here that I enable SSH access directly to the host, the BitScout host system, the live CD system, and you will understand later from the diagrams why it is important. Because I want to have a simulated presence of the owner of the system over SSH instead of just being physically there, because I cannot go to the power plant physically. And the other option is LAN access that allows me to connect directly to the BitScout instance other than using the VPN service that is actually described here. Based on the OpenVPN configuration, this is automatically generated during BitScout build. I'm not going to cover all other options because they are very well described on the website and the source code of the BitScout, so feel free to explore that if you have time. For now, let's start building process. So, like I said, all we need to do is to run automake. Please note that currently we are building BitScout on the latest Ubuntu 2004, and the choice of flavor of the distro was quite obvious. It seems like the majority of users are more familiar with Ubuntu than any other, rather than any other operating system version based on Linux. So we are using Ubuntu here. Also, you need to provide your password, user password, if we are going to build it on this machine. We will need a sudo access, a super user access, in order to install the missing packages and update your software repositories before building BitScout. So it will automatically add packages and tools that are required for the building process. So if you're not comfortable with this, I do recommend running this on a virtual machine. So what's going on now is we are fetching first the indices of the software repositories so that we can see all the latest packages. And here is the experimental part. Given that we are not sure what is in this updated software, so the moment that I am building the BitScout ad is a moment of complete uncertainty, because the software keeps changing by the maintainers of the software, and so does the configuration files of the software, the location of libraries and names of the files, and so on and so forth. And this can of course result in failure of build. So do not get completely surprised if it fails. Just try to figure out like the last based on the last lines of this Webos log and output of the building process, what went wrong. Fix it, because BitScout is just the text-based project based on the shell scripts, so it should be pretty easily fixable if you are familiar with Linux command line. Otherwise, you can wait for the patch from me, because I do monitor the state and the health of the building process pretty much every day, and as soon as it fails building, I will try and fix that for you, so that perhaps it may be as easy as just pulling the latest version of the code from the GitHub. So next, after the repositories were updated, additional tools were installed, there will be the next phase of installing the base tools, which I think already passed, and then the additional tools including Python and many other tools. BitScout comes in 3 flavors. It's minimal, medium and maximum size. So the minimal BitScout comes without any tools at all. You're supposed to install them when you run the live operating system. So they are getting installed in the RAM disk, kind of, and they never touch the hard drive. And basically that is the core rule of BitScout. Never touch the hard drive. Be very careful with this and never modify even a bit of data. So you can install additional tools in the RAM if you're missing something, but you can also save your time, or maybe if you don't have network connection, then you can put your tools right into the live CD root file system. So that comes with the medium and maximum size of BitScout. So medium has a selection of tools that seems to be important for disk acquisition, and maybe the basic triage and analysis of the situation in place, while the maximum comes with the meta package from Ubuntu repository called Forensics-O, and that includes hundreds of different small and big tools and frameworks for forensic investigation, malware analysis, disk recovery, and many other things. So feel free to choose your version. So I am currently building the biggest one. So let's see how fast it gets downloaded and built. For now, let me move on while the terminal is running. Let me just power off the screen and explain you some BitScout mechanics. So BitScout starts from the bootable media, and you can read this diagram from right to left. One big advantage of using bootable media is the reuse of the original hardware where we start this media from. Why is that important? Well, sometimes you deal with very rare enterprise hardware, or maybe not supported, maybe old hardware that is no longer produced, and you just have to use the same hardware in order to boot the system. the code of the operating system may verify the presence of this hardware. It might use keys stored in the TPM module and so on and so forth, or it's just probably unfeasible, to extract the hardware and bring it to another place. So you have to do it in place, like we have to do in our story, because we cannot really extract the hardware from the nuclear plant control room, because it's already contaminated with the radiation, because the plant was abandoned and nobody goes there. So we have to fix it in place. So what's on top of the bootable media? Like, once the media starts, of course it boots our Linux system, which we call BitScout host. That is the operating system started out of the media, and that comes of course with the standard packages and software such as systemd, but also we extended this a little bit with a few things such as privileged commands execution support. So there is a mechanism, inter-process communication mechanism, that allows us to run certain commands after verifying, validating them, run them on the BitScout host. And that signal may come from the layers above, which I'll stop at later. There is also a historian service that keeps tracking all of the changes of the input and output that the remote expert could see on the screen, so that we can reproduce the same steps or prove that certain things were found on this during this analysis session. It is good for the record. So the next layer is the Linux container, based on the nspawn container management, which is part of the systemd. In fact, it is quite lightweight. It's already bundled with the systemd anyway, so we reuse this. And instead of having a separate root file system for the container with all the packages and libraries, we managed to map the original host BitScout host system onto the container in the kind of a read-only mode with a read-write opportunity, where the written files are actually redirected to a different separate storage, so that we can also modify the configuration while running inside of the container without affecting the host system. So this way we save space of the original media, because we do not duplicate files of the two Linux instances running on this bootable media. So of course that also comes with the collection of forensic tools, which become available both on the container and the BitScout host layer, and that is defined by the size of the disk that you decided to build, be it small, medium or large. On top of that, I'm going to show today the usage of the copy on write virtual machine drive. So I'm going to deal with another layer of virtualization based on the QCode2 file format. That is a copy on write file storage, virtual storage, that can be attached to a virtual machine based on the QEMU hypervisor, and can start any operating system that you want if you have the disk image. So in our case, we're going to start it from the image that is actually coming from the original hard drive, through the layers of safety guards. We map these disks in a read-only mode, and with the help of copy on write temporary QCode2 file stored in the RAM, we're going to even enable the write operation on such disk, where the written sectors will be dispatched into standalone file in the RAM and can be disposed at any moment, so that you can restart your experiments with the original failed system at any moment without any risk to harm that system. So if you start the subject operating system, the one that failed in the virtual machine, you can try and recover it using all tools that you can reach out to. You can even install additional tools on the VM itself, using the, of course, they're compiled with the support of the subject OS platform, and that can even further extend your capabilities. Right, enough from this diagram. Let's talk a little bit about how we interact with this over the network. So if you read this diagram from bottom left, and there is an expert, that's you. you need to connect to the live OS. There are two ways of doing this. Default is use your dedicated VPN server. So this is preferable way when you deal with systems remotely and you don't have direct access to the PC over the LAN. Maybe that's the condition for most of the nodes behind the gateway or enterprise proxy. This is where VPN client that is bundled with the BitScout becomes very useful. It was useful to me, I can tell from experience, but if you are dealing with a demo like this, or maybe you have direct access to the LAN and it's just a plain LAN that allows you to interact with the BitScout live OS directly, you no longer need a VPN server, and that's what we are using now. That's what I changed in the BitScout build configuration file, if you remember. So once that is running, you have a shell inside of the container by default, but you can also enable access to the BitScout host, which I also changed and did in the configuration file, because some of the commands require high privilege, and they can be only authorized by the owner of the system or the one who has a shell on the BitScout host. So most of the time we will work inside of the container, and I will show you when we need to get some authorization or support from the owner. So in our case, while being in the container, we see the virtual Ethernet card in Ethernet interface that has nothing to do with the real physical card. We also see the disk mapping instead of the real hard drive device. We can only see a part of the device that is mapped inside of the container, or the whole device, depending on what the user outside of the container decided to give us for analysis. So within this container we can start the VM, like you understand, and interact with this as we need. Alright, so far I think we can move on and get back to our terminal to see if we... Alright, we just finished building. I think a second ago we finished building a... Oops, sorry. We just finished building BitScout. A second ago it was completed. So you can see that there is a new file called BitScout 2004 AMD64. That stands for 64-bit version of the BitScout 2004. And let's see how big is this file. It is 1.2 gigabytes, so that's the largest build of BitScout so far. But of course you can extend it with your own tools, with your own security solutions if you need, your own signatures, and so on and so forth. It is rather easy to do. Let me show you actually how you do this, just the basics of it. So another directory that appeared that has not existed is build.amd64. This is where all temporary files are located now. So if you go here, you can see that there are other subdirectories. We are interested in chroot. So if we list chroot directory, that contains all of our root file system of the BitScout Live OS. So any file that you put here will show up on the Live OS and the container as well. So let's just try and validate this. So let me open a file. To open it as a root, because you see the root is the owner of those directories. So let me open the file in chroot etc message of the day motd, and here we put something like, I don't know, a popular vice phrase, a quote from Bruce Lee, for instance: "Be water, my friend." And yes, that helps. Now, in order to rebuild and make an ISO file, a new one, all we need to do is just start one of the steps from the automake sh file. So let me quickly show you how it looks like. You see that every line here actually is a step in building the ISO file, from the welcome message to fetching of the submodules and downloading chroot and so on. One of the steps closer to the end is the image build.sh. So this is what we want to call in order to rebuild the ISO file. That will be enough to reproduce a new ISO file. So I'm going to call scripts image build.sh. And now it is going to compress in the multi-processor mode, multi-threading mode. It's going to compress the root file system in one monolithic file called filesystem.squashfs that is going to be placed on the ISO file, the container for our disk image. And let me remind you that the ISO file is a hybrid image, so it can be put both on a CD-ROM and on a USB drive. It can also be used both with the MBR-based, the older MBR-based booting configuration and firmware, as well as the newer UEFI-based systems. So we also tested both on PC and Mac, so it should start on your Mac theoretically as well. Sometimes if you have some unusual configuration or setup, it may not necessarily find the original media where it started from, so you might need to modify Linux command line options during the start of the bootloader, and then it can fix the problem and let it start in some non-standard unusual setups. So one of such options I'm going to show you today, later during the demo, if everything works, if we reach to that point. So I guess it's going to go to the 50%, and then it usually jumps over the next 50% rather quickly. So let's see that. The further steps, this is most heaviest probably in creating the ISO file, compressing all the files that we unpacked. Alright, look how fast it starts going after the 50%. So soon we will have the ISO file that is ready to be booted on the remote system. So in our case I'm going to save some time not to show you how exactly we transfer it to the power plant, but for now let's just make sure that our BitScout is built properly. Okay, 1.2 gigabytes, so I think we can start it on the remote system now. So we're not going to see how it is being booted for now, because that's running somewhere on the remote machine, but next step we need to do is to connect to this machine using the SSH keys that were either generated or reused, like in our case. So first let's find where this machine popped up. So we get a scan with a network scanner such as Nmap for the open port 22, sorry, and not use ping, do not resolve the name or IP to the host name. Then we are going to specify the very high speed of scanning and also show only open ports found, and then specify the target network, which in our case will be something like this. And let's see. Okay, some extra dot. We don't need this. Alright, we found a host. So this is our probably our BitScout. Let's see if it works. We can validate this by connecting with SSH to this host. So we are going to use the SSH key from the config directory, but note that the config contains the source files, while all of the export files such as keys and certificates will be placed into the exports directory. So better access it from there. So we are going to use export/export etc ssh scout file that contains the key. We use user called user to connect to BitScout and specify the IP. And here we go, SSH session. Yes, we trust the remote key. We are connected now to BitScout. And as you can see, we also have the greeting from the message of the day file from Bruce Lee, the same that we put on the root file system. So the file that we modified actually made it to the ISO file and to the rootfs. So now what we want to do is to start maybe multiple windows with different SSH sessions to continue. Let me quickly disconnect from here and start a Tmax session so that I have multiple terminals. And let's establish a couple of SSH sessions to the same host. Alright, we can elevate our privileges to root inside of this container with sudo-i with no password for the user. We become root. However, note that this container is running as a privileged user, so this root is in fact something simulated. So it is a fake root, which however is powerful enough to install some software and change files in the etc directory of the container. So we have a couple of root sessions on BitScout. In order to start working, we need to be able to access the hard drive of the failed system. So let's see which drives are attached. We run the lsblk command that lists all the blocked devices on the machine, and we can spot that one of the devices called SDA is a 12 GB disk. One of our devices is SR0, that's the 1.2 GB, the original source for the BitScout ISO or the bootable media. So that one is a ROM type device. But we're interested in analyzing and attaching here to the SDA device. But if you look at the dev directory, there is no SDA device or no SD1 or SD2, which probably stands for the drive C of Windows, the largest partition. So there is no such file directory. And why? It's because by default the container has no access to any hard drive. The owner of the system has to give us this access to authorize start of the analysis and to assign which partitions or which devices the expert can access. So in our case, we are the owner and we are the expert, so we're going to simulate the presence of the owner, like I said, by connecting to the BitScout host over SSH for now. If there was a physical person in front of the machine that started BitScout and that had a screen attached, then that person could see the physical screen that displayed BitScout management tool that allows you to choose which hard drives to authorize for analysis. So for now, let's just connect to that session remotely, and if you remember, I have enabled this connection to host over SSH. So the principle is the same as connecting to the BitScout container. All we need to do is just change the port. Other than connecting to the default port 22 for SSH, we connect to the port 23, which is not Telnet service port. In our case, we just put an SSH service that is running on the BitScout host. Let's connect there, and you can see that the name of the host has changed from BitScout, as it used to be here, into BitScout-host, which indicates that we are running now on the host. I'm going to elevate privileges to the root, and now we are real root on that live OS. And I'm going to start the tool called Scout Manage. that is also running now on the physical console. It displays a little bit weird now here on this monochrome screen. Apologies for that. The colors are not very contrast, but well, we can see and read the menu here. Basically, what we need to do is to go into the disk submenu, and we need to map the device to the exports container. So we choose map the device, we choose which device we want to map. In our case, this is the disk of 12 gigabytes, the SDA device. We are going to map as a read-only evidence 0 device on the container. And also to show you another feature is that we not only can we map the whole device, but also separate partitions can be mapped. In our case, let's pick the biggest one that contains the Windows file system, the SD2 with the system files, and map it into another device such as Evidence1, for example. So once you map this, you can view all mappings in the View subcommand, and you can see that SD is mapped as Evidence0, SD2 is mapped as Evidence1. Let's explore this from within the container. So now, if we try to list the dev host Evidence0, this block device will have the whole disk mapped as read-only. So we can even try and view it with a hex editor or even modify something on it. So if we try to change something, let's say replace some bytes with zeros, and pressing Ctrl X offers us to save changes and quit. I say yes, it says operation not permitted. So you cannot really modify this device. You have to press Ctrl C and exit the editor, and then going back shows that bytes are unchanged in fact. So alright, this write protection works. So what we can do next is, of course, you do have access to the hard drive as you see now. So if you're interested in forensics such as standard operations, disk acquisition, you can start working with this device right away because it contains all 12 gigabytes. Let me show you this. That's the size of the device in bytes. It contains all 12 gigabytes of data, so you can start running your favorite disk acquisition, disk cloning tool. Maybe it's just regular DD, the disk duplicator tool, and acquire an image over the network or on the attached removable writable storage device. I'm going to show you how to attach writable devices later, but for now you should know that you can start working on this immediately. And if you have the partition mapped as well, you can even explore what is on the the partition itself with the FLS command, which comes from the sleuthkit package, a forensic package on Linux, with some options such as list all the directories recursively in the lone output format for each file. So if I put here evidence1 and type it to less, we can see the directories and metadata of directories and files that are standard on Windows. You can see the users directory here, some of the other standard directories, users public, users user. So these all are coming from the Windows partition, system partition. Apparently there's a lot of software installed, and you can explore the file dates, file sizes, and the file nodes on the left. This is where you can already do some triage and look for files based on their file naming, file timestamps, and so on. We want to reproduce the blue screen. We want to confirm that it fails on boot and try to fix it. So we are going to achieve this by starting a virtual machine that runs this system inside the VM, but the drive is the actual data from the hard drive that we attach in the read-only mode. So let me show you how to do this. In order to save some time, for the lengthy commands that I need to type and for all my typos corrections, I'm going to use some notes file where I put some of the commands here. So we start from this command, which is QEMU image create, that creates a new virtual machine disk drive, which is mapped to the backend file dev host evidence 0, our original read-only accessible hard drive that contains all data from the physical disk. So now we created this file, evidence0.qcode2. It was the last parameter in the command line, and that contains less than 200 kilobytes of data. So this is the file that is mapped to our block device. So whenever the operating system tries to write something to a disk, it will the data will go into this file, evidence0.qcode2 file, which is placed on the RAM disk of Bitscout. So if you power off Bitscout at any moment, none of the bytes will be transferred to the hard drive, so it is safe to interrupt Bitscout at any time, power off the system if you want. Also, you can remove this file and recreate it from scratch in order to start from scratch. Next, we're going to start the VM right away. And this VM, let me show you a moment. Copied the wrong line. Going to start VM. That's a bit lengthy. I know that's the maze of command line options of the QEMU system, the VM software, the hypervisor. This is 64-bit hypervisor that leverages the hardware virtualization via KVM module. It uses the same CPU configuration as the host system. We use 512 megabytes. Remember, this is important. 512 megabytes of RAM. We boot strictly from the evidence 0 drive, so from the virtual hard drive, and we attach the monitor. It's kind of a console to control the VM. We start VNC and SPI service. That one allows us, both services allow us to access the physical the console, the screen of the video adapter of the virtual machine. The video adapter that is emulated is of time VMware, and we also start a network interface so that we can exchange some data with this virtual machine or the network, Windows network sharing. So that's why we specified also the user network and the SMB server to be started on IP 10.024. We will access this, I'll show you later, in order to transfer some files back and forth from Bitscout to virtual machine, and that will be useful to extend our virtual machine Windows instance. So note that I'm going to map the SMB share from root /SMB directory, which does not exist here. We just started this live OS. I'm going to make this directory first, and now I'm going to run the VM. Once the VM is running in the background, I'm going to connect to this quickly using remote viewer command from my current expert machine. So when I do, you can see that Windows is already starting. And let's confirm if it has a problem or not. So now the VM is booting based on this evidence0.qcode2 file that when the read operation comes, it provides data from the original drive. Alright, we can confirm there is a blue screen, there is a fault at Windows. Some technical information shows us that the problem is in fact in floppy disk driver flpy disk.sys. So that could be our culprit. For analysis, we can try and remove this driver if it's not mandatory, if it's not critical one. We can try and delete it and start Windows without it. If it is a critical one, we have to perhaps repair it or recover the working version. So for now, Windows cannot really recover this file, and if the startup repair does not help you, which happens in many cases, you have to repair it manually. So for now, I'm going to close this session, and I'll show you how to access this read-write accessible virtual disk through BitScout. So right now, Windows tried to boot, and it already written 84 megabytes to this virtual disk. Maybe some logs, the crash dump, kernel crash dump was written there, and so on. So what we want to do is to connect to this drive and explore its file system and deal with it. So one way is to use QEMU NBD tool that can create and expose this disk via the virtual block device. However, working with block devices and mounting command requires some privileges. When we run inside of the container, that can be challenging because we need kind of approval, authorization for the privileged commands from the owner. So it's not as easy as just starting another BitScout and using full root access to the evidence 0.qcode2 file. So that's what I'm going to show you now. We will start BitScout within BitScout. So we're going to run another live OS inside live OS on a VM and attach this evidence 0.qcode2 file as the hard drive to be changed. So let me show you how we do that. In fact, it is rather easy. We just modify basically one option that we need to change. I'm changing just option of the CD-ROM, which I mapped from the dev SR0 device. If you remember, SR0 was our source media for BitScout, and that will be used as a CD-ROM. So we're going to start this system now. We also have the evidence 0.qcode2 file attached to the hard drive, which we don't use as the bootable device. So we start from the virtual CD-ROM. So let me show you how this works. I started, VMware is running, going to another terminal, connecting to the console, and this is what I see now. So if I press the cursor keys up and down, I stop the ticking timer before it automatically boots into the BitScout so that I can explore the menu, and also I want to actually boot the failsafe BitScout node. Why? Is because this screen by default, the default mode of booting BitScout puts us in a too high resolution, smaller font. So in order to see this from the demo, I'm going to use the lower resolution that comes with the failsafe mode. So next, like I said, you can modify Linux command line boot options from this bootloader menu. It's a grab bootloader. I'm pressing key E on the keyboard, and here is a simple text editor that allows us to modify the command line of Linux kernel. So I'm just going to change the root partition, root device into SR0. That's our virtual CD-ROM where we started BitScout from, and press Ctrl X to start booting these options. Okay, now it's going to unpack the additional files, including modules and startup scripts, and start booting BitScout. So this is what the owner of the system sees on the physical console once BitScout is being started. There is a file integrity check. It's part of the process. and then it should boot right into the BitScout management tool, so that we can see the simple text UI interface where we can choose, modify some settings, connect to a network, and provide disk for analysis. So there is no graphical interface because it saves a lot of space. That's why there is a just text UI simple interface running in the text mode. So remember last time we used the disk menu. This is where we could see our devices and map them to the export into the container. Right now we are running on the VM that does have the same disks. There is no mappings as of yet, and we run as the owner of this system. So basically we don't need the export session here. We just open the shell as root on the BitScout host, and we work with the attached devices directly. So how do we do that? I remind you that we are looking for the bigger partition, the SDA2, which is a virtualized mapping that contains the data from the original subject system. So first we enable the write access because we're going to modify some files on it. That comes with block dev set rw option. Enable read write, and then we specify the path to the device. Once we did that, we can mount the partition to a directory. First we create a directory, mntc for the drive C, and then we mount the dev sda2 onto mnt/c. The disk wasn't shut down cleanly, so hopefully it is fine. That's because apparently we crashed on boot. But if you go to the mntc, we can see that there is standard Windows directories and files that exist there. They are read-write accessible to us, so they can fix Windows if we know where to fix it. We already saw that the failing driver was a floppy disk driver, so let's go to system32 drivers directory. And let's see if this floppy disk driver is here. Apparently it is there, yes. So let's just move it to a side so that it is not used during boot. So a very easy fix, I renamed the driver. I have renamed it, adding underscore in the end of the extension of the file, and this is enough. I think we can just try booting Windows again. So what we do next is we unmount this partition cleanly, right, we sync the disk, and we no longer need BitScout. The data has been changed, and it has been changed not on the real physical hard disk, but on the virtual evidence 0 hard disk. So I can easily quit the VM now. Let's see, the size of the evidence 0 is 1.46 megabytes now, maybe due to some fixing in the file system. And next we will boot the Windows VM again, so previous command will help us here without the CD-ROM attached. Okay, started, and let me connect and choose start Windows normally. Let's hope for the best. So now let me remind you that we have removed the driver. Windows now starts all the drivers required for the system to operate, and it will just miss the floppy disk driver, which is not essential for Windows to operate. So that driver caused us the blue screen. Removing it might fix the problem. Let's see. It offers us to check the disk. Well, for now we can save time and skip checking the disk. But yes, we got the graphical interface working. That means that that driver was the issue that we resolved. Now we need to log in into the system to make sure that everything is working fine. And here you may have another challenge. Maybe the administrators forgot the password, or maybe it was changed by the attackers who actually crashed the system and make it unbootable. So how do you log in without knowing the password? One way is to use CHNT password tool that comes with BitScout. You can modify system password database when you put it into the BitScout previously, and that will allow you basically to make a user administrator and reset any user password. But let's do another trick this time, and let's just do a trick to bypass this password authentication, to reset the password right from this WinLogon screen. Because we have a privilege of accessing the virtualized physical RAM of the VM, because it's running inside of our hypervisor. So we're going to use this access and to patch the brains of Windows in order to log in without knowing password. Let me show you how to do this. For now I'm going to close the remote session because we are going to work with the hypervisor to patch its memory. So QEMU here is running, as you can see, so I'll keep it running so that machine is fully alive as we patch its memory. Let me just find the QEMU process. So we can see that QEMU process is running here as root with the pid 403. So we are going to go into the virtual file system /proc 403 for the PID, and here will be a bunch of files. Let me zoom in. So a bunch of files, one of them is called maps. So the maps file contains memory regions inside virtual address space of our process, QEMU process. So you can see on the left hand side there is the beginning and the end of these memory regions, followed by some properties like read, write, and so on. And there are quite a few of these memory regions here. Some of them are mapped to the libraries loaded from the disk required for the process to work. Some of them are located for the stack, for example, of the process, and so on. So we need to find the memory region that is 512 megabytes in size, and that's, if you remember, the size of our virtual machine that we started, our guest OS that we started within the QEMU. So how do we find that? Basically we just need to take a value on the left and subtract the value on the right in the left hand column, and just sort it by size and find 512 megabytes here. So I'm going to do this manually. Instead we're gonna use a tiny command line on Linux that allows us to do this quickly. Let me just copy this part of the command line. So next I'm just cutting maps file, piping it into this command line. That gets the first field separated by space, and then splits this field separated by the dash line. It gets two numbers and subtracts one number from another and prints it to the output that is getting sorted, and we can see the sorted list with the ranges. So on the bottom of this list you can spot 536 million of bytes, and that actually fits into 512 megabytes of virtual machine RAM. So our RAM starts from this address, virtual address space address of QEMU process. So now we're going to patch QEMU process live. So I'm going to open the memory of QEMU process that's in the mem file of this directory, and I'm going to jump to this address. Press enter to jump to a new position, paste this address, and here we go. This is the beginning of our virtual machine, virtualized RAM. So whatever we write here goes into the virtual machine. So what are we going to look for is the on-screen keyboard. That one we can call from the Windows logon screen. And instead of calling on-screen keyboard, we're going to redirect it to call some other useful tools, such as Windows command line. So let me show you how you do that. So calling on-screen keyboard is done like there will be a reference to the on-screen keyboard executable, which is osk.exe, but that one is written in Unicode, so we get to convert it to Unicode first. Let me maybe do it on another shell. So let me go to some free shell and maybe do it here. So I'm just echoing without the new line the string osk.exe, and I want to convert it to Unicode, basically just appending 0 bytes after each ASCII character. As easy as that, but let me do it through the iconv tool, the encoding conversion tool, converting from UTF-8, which is current encoding, into UTF-16, the 16 bits Unicode encoding, and I'm going to pipe it to the XXD to get it hexified so that we can see hexadecimal values. We skip the first 2 bytes, which is the standard header for the Unicode UTF-16 string, and I'm just copying this, which is exactly osk.exe in the Unicode notation in hex. So next I press in this hexadecimal editor, I press slash to search for a pattern, and I paste this pattern. So here I'm going to skip this one, osk.exe DLL. It's some chunk of the string somewhere. Not sure what exactly that is for, but I'm going to show you how to find the right one. There is a very simple anchor string that is preceding the osk.exe. Skipping this one too, osk.exe.mui, not our thing. That's not our thing. Skipping this one too. And this is not what we're looking for. Skipping this one too. Let's see, that's not it. Close enough, but not it. And let me see. This one looks like the right one. Let me check. This seems to be the right one because the notation it's written in is it's kind of the templated, the environment variable system root and then system32 osk.exe. That's probably the right one. I hope so. I'm not sure. There was previously there was a little bit different. Let me check further just to double check. Okay, I think this contains also the templated path, but this has an important keyword here, start.exe. That's what we were looking for. The start.exe, it's part of one of the modules that is used during the WinLogon screen that tells to start executable whenever this option is enabled. So this is probably the right location. So what I'm going to change now is I'm changing OSK into CMD. Simple as that. 3 characters into 3 characters. OSK to CMD, and that's it. Next I press Ctrl X to exit and save, confirming that we want to save. Yes. Now we already patched the memory of the virtual machine that keeps running there. So let's get back to that virtual machine and see if it works. So one issue that you can find is the desynchronization of the mouse cursor. If you do have this problem because of various acceleration and speed sensitivity of the mouse, you can try a quick solution by changing the protocol from SPICE to VNC. SPICE is preferable because you can even attach the remote devices and directories of a SPICE, but for now let's switch back to VNC. So all I need to do is change in the command line for remote viewer tool, specifying the VNC protocol and different port. So I started this on 5900 of the same IP. So let's see if the mouse works. Now it's a little bit better, as you can see. Not perfect, but more or less workable. So I'm going to use this ease of access feature, and I'm going to enable the on-screen keyboard. So, OK, brings me a shell. So let's see who we are in this shell, and that is anti-authority system. So we can do anything we want with the system privileges with the user database. So we'll just quickly change the password of our user. User 12345. Command completed successfully. That means the password has been changed. Now we can also check who is this user, and if it's not part of the administrators, we can add the user to administrators group as well to make it easy for us to have high privileges. Now we no longer need the on-screen keyboard. We can disable it because it will be annoying pop-up otherwise, and we can log in with a 12345. Apparently Windows is not activated in year 2060. There is no activation service online, and it has been reinstalled at some point. So we're gonna skip these pop-ups for now. And here you go. You get some message from the blackmailers. There is a new network available because we attached a new network interface to the VM. So a message says here that we need to pay 100 Apocalypse coins in order to get the data back. Apparently the system was attacked. It was not just a random crash. So let's see if there are any signs of malware activity. At least checking the basic things such as passive listening backdoors running on our system. So let's start a shell as administrator and do a quick check. What we can do is to run netstat with the ATN options to list all TCP, all listening connections and established connections, and go through the list of it. What we can quickly spot is this listening port 1337, which is a lead port used by many malware. So how do we find the process which created this? We just add option B, which shows the binary responsible for the open port. We scroll up, we can see that 1337 is actually owned by a process called ctfmon.exe, which sounds like a standard process on Windows, which for some reason opened that process, that port. So it's possible that that process had a memory injection, some malicious memory injection, and we need to check what it was. So for this we will need tools. Let me show you how you can copy tools here. Just open the Explorer and you can go to the network share that we previously started on BitScout container. So if you remember, this address we used for the network share server, and there is a QEMU directory which can be used to exchange files back and forth. Of course, you can place your Windows tools here. For now, I'm just going to show you the proof of concept that, let's say, new directory 123. We just created a directory. I'm going to show you that it is immediately created on BitScout. Just disconnect from here and go back. to the root directory and show you the contents of the S and B directory. You can see that this directory was created. So you can, every file that you place here, every directory that you place here, your magical AP on that VM, and we can copy some tools using this exchange mechanism. Now, for the sake of time, I'm just going to use a tool that I placed in the tools directory in advance. That is a process explorer that I'm going to start as an administrator that allows us to see properties of all processes. And I'm going to find the ctfmon in the list. Here's our ctfmon executable. Apparently it is running on port 1337. So that confirms that this is our malicious process. And you see that the executable is placed in C Windows directory, and the command line includes a reference to another file, wtr9001.tmp, and there is a port probably to listen on. So we can try and locate these suspicious files, so the ctfmon.exe and wtr9000.tmp. We can remove these to prevent malware from starting, regardless of how and where it is started. That should be efficient enough to disable malware, to disarm this malware. Otherwise the attackers can come back and break the system again. So for now, let's just rename our ctfmon.exe into ctfmon.exe.pac. .pac. Okay, renamed, and now let's rename our wtr9001.tmp into the same with .pac. This one says that the system cannot find the file specified, like wtr9001.tmp does not exist. Is it really so, or is this just some trick played by the malware? So one of our favorite tools here in the year of 2060 is Notepad, that helps us to validate such things and discover rootkits. As you can see here, the file has some contents, although it does not exist on a disk. Notepad by this confirmed that we are probably dealing with a rootkit that somehow hides the file from the file system and doesn't let us access it or see even that it exists on a disk. Let's double check that it doesn't actually have a hidden attribute. So with a dir/a we should be able to see all files even if they are hidden, but the file is definitely not there while Notepad can see it. So what we can do with this is, well, we can easily just corrupt this file if we don't need a copy of it, or reboot from BitScout and get a copy of it before, and then we can deal with this. So for now, let's just destroy the file. Simple as writing something to it with the echo command. Make sure you type the name of it right, otherwise you will miss. It complains that the file is being accessed, so as long as it is loaded in the RAM, we cannot really modify it. So let's just kill the process of ctfmon that probably has it loaded. If we are allowed to kill the process, we should be able to write to this file. Voila. So it worked. Now I think we have changed the file. We can validate this with the Notepad to see the contents. You can see that one was written to a file, it's no longer executable file. So I think it is safe to leave this system for now, unless you want to continue and find the rootkit. I'll leave it as a homework. So let's just make sure that the system can boot freely without a problem. Remember that we have changed the password. Now we know the password is 12345. Maybe you can choose a better one if that is a real system, not a demo one. But so far we can provide the original administrators and the owner the access to the system, which is recovered after the blue screen rising on the boot, and even has some malware disabled. At least this is the basic things we can do. Of course, the system after the infection better have to be reinstalled. However, for now, if it's mission critical, it can be used right away, maybe with some additional security checks and tools run on top. Right, it managed to start, so I think that it is safe to say that we have fixed the system. So what's next? Next is we are going to maybe nicely shut it down. If we go back again, and proper shutdown is here. So once Windows shuts down, the virtual machine shall exit. Let's confirm. As you can see, the QEMU system process is not running anymore. So what we can see in this directory now is that the evidence0 qcode2 file is 258 megabytes of changes written to this virtual disk. Now we need to commit these changes back to the underlying physical drive so that we can persistently store these changes to the disk, fixing the system essentially. So for this, let's go back to our notes and just copy a couple of commands. So one of the commands that we need is this QEMU image rebase that will allow us to redirect this evidence0 device from the one backing file to another. So instead of pointing this to the evidence0 device, we are going to change it to the storage0 device as the backing file. Once we run this command, the QEMU image goes through every sector that is present both in storage0 and evidence0 that were changed by the evidence0.qcode2 file, and make sure that they are identical. Otherwise it reports an error. So if the sectors are identical, only then the change file, which is evidence0.qcode2 file, can be rebased. So it'll take a little bit of time to validate all 258 megabytes of disk sectors that were changed, and soon we should see that the process finishes. Let's give it a few more seconds. Alright, this is done. So if we list it again, we can see that the file size hasn't changed, but if we run file tool on it, we can see that the backing file has changed from evidence0 to storage0, which is exactly what we need. So next we need to commit these changes to the backing file. Copy this. And when we run this, all the changes are written to the disk. Now the image is committed. That means the change file no longer contains change sectors, and what we see here is it was reset to 256K, which makes it essentially empty. So all changes now are permanently written on the underlying disk. This is the critical change for us. So once we do that, we can confirm that this actually worked and the changes were applied. For this, we can mount the drive C and see that it contains changes we made. So for this, let me show you another trick how we can mount the file system on BitScout using the privileged commands, mounting commands, and zoom in one of the terminals. So let me remind you that we do have our device in SDA2, and if you want to mount it, let's create a directory and then C /C_RO, and this is where we're going to mount drive C. If you remember, we did have a block device mapped specifically for this purpose. So we have evidence 1 that is mapped from dev SDA2, that's the second partition on the disk, which contains the drive C. So that's what we will use. So to mount a block device to a directory, we can run just the mount command, specify where we mount it from. Instead of SDA2, we're going to use host evidence 1, and we mount it to C_RO directory. So running it like this is going to fail for two reasons. Well, first of all, mount operation is privileged, and also the evidence 1 is read-only device, while a mount is trying to open it in the read-write mode first. So well, it automatically changes to the read-only mounting, which solves the second problem. But the first one, where our limitation is we cannot mount any file systems using kernel modules, because we are running in the unprivileged container, so we don't really have this privilege. Now, what can help us to have this privilege is special mount tool called mount.priv, the one that is going to tell our bitscout host, please mount this thing onto that directory for us. And you have to be precise with the file system selection, as well as specifying that you want to mount it as read-only. So then it may listen to you only if the privileged execution mode is enabled and such operations are allowed. So with this you need an approval, authorization of the owner of the system. It's in the same disk submenu. There is a privileged mode submenu, and if you go there, it is disabled by default. So we're going to enable it for now, as if the owner permitted us to run these privileged operations. So if I repeat this again, you can see that this time the mount operation worked properly. Let's verify that. So if you just list this directory, yes, we can see Windows directories and standard Windows files. So we can what we can validate is, let's say, just take this file that we modified, the malicious file. You can see that it is very small, and in fact, if we open it on terminal, it just contains one character, digit 1. So that's exactly what we have written to this file, which confirms that our changes were applied to the real disk of the broken system. Alright, I think that is enough. To make sure that all changes are preserved properly, we need to nicely unmount the file system. And please note that you cannot do this with a regular umount command, because you need to use its .priv version that will run on the host. That's a privileged operation as well. So once we do this, we can sync the disks, and I think this is safe now to power of bitscout. So you can just turn off the power and the system shall remain fixed, or you can issue the shutdown command from the privileged user. So there is a shutdown command for this. The bitscout shall start shutdown process. This is it. I hope you liked this demo. We have many more demos. We have actually 2 full-day trainings for bitscout, doing all kind of magic with steam and smoke tricks, dealing with proprietary disk encryption, full disk encryption, working with UEFI modules, NDR, encrypted partitions, and so on, dealing with all kind of tricky malware. If you're interested in that, please follow me on Twitter. I'm going to announce new trainings there, or go to the bitscout-forensics.info website, where you can find some pre-built images where if you want to experiment with them without building your own image. You can also find some details, documentation, instructions, and even ASCII video demos of certain basic forensics procedures that you can do with the help of BitScale. There's also a slight comparison with existing solutions that exist out there, and basically we are looking forward to extending our community. If you find this project interesting, please subscribe on GitHub, propose your changes, and let's form a community and push this forward. With this, I would like to thank you everyone for listening. I'd like to give some credits to these amazing artists that did the graphics all over the internet, and hope to see you somewhere someday. Thank you. Bye bye.